Imagine looking up at the night sky and seeing a bright, reddish dot. That is Mars, our neighboring planet. For centuries, it has been a subject of stories and dreams. But today, that dream is closer to reality than ever before, the dream of humans living on Mars. We are no longer just asking if we can go, but how we will survive and build a home there. This is not just about planting a flag and leaving footprints, it is about building cities, creating communities, and becoming a multi-planetary species. However, turning this grand vision into reality presents us with one of the greatest engineering challenges humanity has ever faced. The problem is that Mars is an incredibly hostile world. It is not the friendly, red desert we sometimes see in movies. First, the temperature is freezing, averaging around -80 degrees Fahrenheit, cold enough to freeze carbon dioxide. Second, the atmosphere is dangerously thin, about 1% of Earth's, and it is composed mostly of carbon dioxide, which is useless for human lungs. This thin atmosphere offers no protection from the sun's deadly radiation, which would bombard the surface and any settlers with cancer-causing particles. And if that was not enough, Martian dust storms can engulf the entire planet, lasting for months and blocking out the sunlight. So, how do we build shelters strong enough to protect us from these extreme conditions? The old way of thinking was to send pre-built habitats from Earth on giant rockets. But this idea is almost impossible. The cost of launching just one brick from Earth into space is astronomical. To send all the materials for a single house, let alone an entire city, would be financially ruinous and logistically a nightmare. It would require thousands of rocket launches. We need a smarter, more efficient solution. We need to learn to live off the land, just like the early pioneers did. But on Mars, the land is red dust and rock. This is where a revolutionary technology, already changing our world here on Earth, comes into play: 3D printing. The big idea is simple yet profound. Instead of bringing our houses to Mars, what if we could build our houses on Mars, using the dirt that is already there? You have probably seen a 3D printer, a machine that creates a physical object from a digital file by laying down thin layers of material, one on top of the other, until a complete object is formed. People use them to make everything from small toys to custom prosthetic limbs. Now, imagine scaling that technology up, massively. Instead of using tiny spools of plastic filament, we would use a giant printer that uses the soil of Mars itself as its building material. This soil is called regolith. Martian regolith is the fine, dusty, crushed rock that covers the entire surface of the planet. It is the reason Mars looks red, as it is full of iron oxide, what we commonly call rust. For a long time, this regolith was seen as just a nuisance, something that would clog up machinery and cover solar panels. But scientists and engineers now see it as the most valuable resource on the planet. It is the free construction material that is already waiting for us, scattered across the entire Martian landscape. We would not need to mine it, we would just need to scoop it up. But you cannot just use loose dust to build a strong wall. So, how do we turn this powder into a solid, durable building material? The process is similar to how we make concrete here on Earth. The most promising method involves taking the regolith and mixing it with a special binding agent. Some proposals suggest using a sulfur-based concrete, which would be heated to melt the sulfur found on Mars, acting as a glue for the regolith particles. Other, even more advanced ideas, involve using a process that essentially microwaves the regolith, fusing the dust particles together into a solid, ceramic-like block without needing any extra ingredients from Earth. Think of it like using a laser to turn sand into glass. The robotic 3D printers would be sent to Mars ahead of the human crews. These robots would autonomously roam the building site, tirelessly scooping up regolith, processing it, and then extruding it layer by layer, following a pre-programmed digital blueprint to construct walls, arches, and domes. The ink for our Martian cities is literally beneath our feet, free for the taking. So, what would a 3D printed house on Mars actually look like? It would not look like a suburban house with a slanted roof and a front lawn. The design would be dictated by one thing above all else: survival. The architecture must be engineered to protect human life from the deadly environment outside. This means the structures will be strong, sealed, and strategically designed. First, let us talk about the shape. Many designs feature domes or low, rounded structures with thick, curved walls. Why? Because curved walls are much stronger than flat ones. They are excellent at distributing pressure and withstanding the immense force from the Martian atmosphere pressing down on them, even though it is thin. A dome shape also has no corners where stress can build up and cause cracks, making it a naturally sturdy design. The walls themselves would be incredibly thick, perhaps several feet deep, to provide a robust shield against cosmic and solar radiation. This thick layer of Martian regolith concrete would be our primary defense, acting like a natural mountain that absorbs harmful particles. The interior of these habitats would be a carefully controlled oasis. They would need to be completely airtight, maintaining a breathable atmosphere of oxygen and nitrogen at a comfortable pressure. The structures would be multi-layered, perhaps with a double shell design for an extra safety margin in case of a micrometeorite impact. Inside, the space would be designed for efficiency and psychological well-being. We would not have large, open spaces just for the sake of it. Every cubic foot would have a purpose. The lower levels might be for farming, using advanced hydroponics to grow food under artificial lights. The living quarters would be compact but comfortable, with shared common areas to foster a sense of community. Windows would likely be small and made of thick, multi-pane glass, or they might be replaced entirely by high-definition screens showing live feeds from the outside or simulated views of Earth's landscapes to help combat feelings of isolation and confinement. The entire habitat would be a masterpiece of bioregenerative life support, where plants, humans, and technology exist in a closed, recycled loop. Building these intricate habitats will not be done by astronauts in spacesuits with trowels and cement mixers. The conditions are far too dangerous for humans to be outside for the long, laborious process of construction. The initial work, the heavy lifting and the foundational building, will be done entirely by an army of smart, autonomous robots. This robotic construction crew is the key to making a Martian city possible before the first human ever sets foot on the site. This crew would consist of different types of robots, each with a specialized job, all working together like a perfectly coordinated team. First, you would have the site prep bots. These would be large, rugged machines, similar to bulldozers and excavators, but fully autonomous. Their job would be to land on the chosen site, perhaps a lava tube or a large, flat plain, and level the ground, dig foundations, and prepare the area for building. Next, you would have the material harvesting bots. These are the miners. They would be equipped with scoops and drills to continuously collect the Martian regolith and deliver it to a central processing unit. The heart of the operation would be the 3D printer bots. These are the master builders. Some concepts involve massive, gantry-style printers that move on tracks, slowly printing an entire habitat in one go. Other ideas propose smaller, swarm-like printers that work together, almost like termites building a giant mound. They would take the processed regolith concrete and extrude it, following a digital blueprint with incredible precision. They would print the walls, the floors, the ceilings, and even the interior tunnels that connect different modules. Alongside them, inspection bots equipped with cameras and sensors would constantly scan the growing structure, checking for defects, ensuring the layers are bonding correctly, and making sure every detail is perfect. This entire symphony of machines would work day and night, unaffected by the radiation or cold, building is safe, ready to move in home for the human pioneers who will follow. The first 3D printed habitat on Mars will be a monumental achievement, a single, small dome standing alone in the vast red desert, a tiny bubble of life in a sea of emptiness. But the ultimate goal is not just one shelter, it is a city. A self-sustaining civilization. So, how do we scale up from that first outpost to a true Martian metropolis? It begins with replication. Once the first robotic construction crew is on the ground and operational, we can send the digital blueprints for more structures. The same machines that built the first habitat can be reprogrammed to build a second one right next to it, and then a third. These initial structures would be connected by 3D printed, pressurized tunnels, creating a small network. One dome could be the living quarters, another could be a scientific laboratory, and a third could be a large agricultural bay producing food and recycling the air. This cluster becomes our first sustainable base. As more humans arrive and the population grows, the construction robots would become even more advanced. They could start building larger, more ambitious structures. We could see multi-story buildings, also 3D printed from Regolith, with internal frameworks perhaps built from metals mined from Mars itself. Entire city blocks could take shape, with specialized districts for industry, research, and living. The city would need large, centralized life support systems, massive underground water extraction and storage facilities, and huge fields of solar panels or even a small nuclear reactor for power, all built and maintained with the help of advanced robotics. The final vision is a city that is not just surviving, but truly thriving. A city that can produce its own food, water, oxygen, and building materials entirely from Martian resources. A city with a growing population of scientists, engineers, artists, and families. The 3D printed regolith structures would form the bedrock of this new society, its protective shell. This technology does not just offer us a way to build shelters, it offers us the key to becoming a permanent presence on another world. It transforms the dream of cities on Mars from a far-off fantasy into a tangible, achievable future, proving that humanity's greatest tool is our ability to use the resources around us to create a new home, no matter how distant the stars.